All right, perfect. So I'll start. Today we're going to have a talk from from Chester. So Chester is he did his bachelor's education, Bachelor of Science in Computer Science at KNUST. I think he graduated with the first class. This was last year, if I'm correct. And then he was actually a Mastercard scholar at KNUST in the computer science department. And he wrote a very nice bachelor thesis, I would say. And then after that, they published a very nice paper from his bachelor thesis, which has started somehow. I feel it has really started his career path. He's currently a visiting researcher at Toyota Technology Institute at Chicago and working on sign language processing and also being involved at the Johns Hopkins University as well under supervision there. And some of the papers, I think the first paper they did, which was on the machine translation for African sign languages, actually was won one of the best papers at the ICLR last year. And this is what I personally got to start listening and watching, following some of the work he's been doing. And yeah, since then they've done some JW sign language as well. I've seen another paper just recently on the sign musketeers, all in the area of sign languages, which I feel is one of the things that maybe is missing, or some of the areas that are missing in the NLP space, is this aspect of sign languages. So we are very happy today. We have Chester with us. Of course, when he starts, he's also going to say some things about himself, and then we can get to interact and learn about some of the things and how we can also maybe start seeing some of these technologies in our tools immediately. All right, so Chester, um, you are welcome to go ahead. He's going to talk on automatic signed language processing, data sets, and then methodologies as well. Please go ahead with your talk, please.
Sure. First, I want to thank Professor Mu for the invitation. And I think I was in Ghana, Ghana NLP was really was a big inspiration in my work. And Professor Mu and Dr. Paul Anzure, they really inspired me a lot when I was an undergrad. So I just want it's really a privilege to come back at this series of talks then basically, yeah. So just about me, I'm Shester Gueuwou, and I completed my bachelor's in computer science at the Kwame Nkrumah University of Science and Technology. And yeah, and we had our graduation last year, 2023, basically. Right now, I do research at the Toyota Technological Institute at Chicago. And for this summer, I moved to the Johns Hopkins University just for the summer, yeah. And my main interest is in computationally modeling what language means beyond text and speech. I'm sure all of us, when we say language, we think of text, or we think of words, or we think of speech, but there's language beyond this type of modalities, and I'm just interested in modeling them and knowing how the computer can understand this type of languages, yeah. So just to give you a motivation of my research, why maybe sign language in the first place, processing is, I grew up with a lot of deaf people during my childhood. Yeah, I remember I was just seeing a lot of deaf people around me, and I was always striking okay, well, how can I help them? But I think the real thing that really marked me to really enter this field was I was my final year in KNUST. I was really looking for a project, and I met Marco Nyako, Mr. Marco Nyako, who is a lecturer at KNUST. And when I met him and I saw his story of how he was saying how his best friend died because he went to the hospital and the doctor misinterpreted his sickness description. Thus, they produced a wrong diagnosis, and later on, that contributed for the death of his best friend, who was also like a deaf person. I was really struck by that, and I was wondering how these language barriers really, really disadvantage some part of the society. On a technical point of view, I have high interest in vision language models and multimodality. I really believe that's the next big thing. Yeah, so I just think this type of research I'm doing helps me get a lot of understanding about the vision and language, how they are related to each other. And we might all know about the transformer, which really like put the whole research AI thing. But the transformer initial goal, the first paper was just to do machine translation for text, basically, which is like a sequence to sequence. And later on, it found itself to have so many applications. So sometimes you do a research on a very narrow field, and later on, the research goes to a different dimension. And perhaps I'm thinking advancement in sign languages or visual languages, perhaps translation will bring again the next big thing. So just to clear some thoughts about sign languages. So you have a lot of false assumptions about sign languages. I'm sure some people have heard how there's a glove you can put on you and it can track the movement of your fingers and it will translate sign languages. That's it. But no, it has proven not to be true because fingers are just like a very, or hands are not, sign language are not only vehicle by the hands. Facial expression counts, body movement counts, and gloves can detect that and they can track that basically. And lots of people have been tweeting about this. We always about how there's always these perceptions people have about sign languages which are not true. And people sometimes write about it or they publish about it, and then we realize that they are using sometimes some offensive languages when they want to speak of deaf people in general, or they marginalize them. Yeah, so just wanted to clear that too. But why is sign language translation really a challenging task? We might ask ourselves. And that was last year, I think just a few months before my graduation. A few months also after the whole ChatGPT came out and we thought the world was changing forever. And I saw just this tweet of how mod, um, someone asked AI to make a sign language manual in case you worry that we will all be about, we will all be out of a job soon. So basically, like these models you have right now are very bad in hands, basically generation and things like that, because hands are really complex when you think about it. The amount of things you can do with hands, the type of shapes you can do with hands, they are really, really, really complex. And it just made me thought like, wow, this is interesting. These models can generate a whole lot of bunch of things, but they can't even generate accurate hands. Sometimes the hands have 6 shapes. Sometimes the shapes are really abnormal, have 6 fingers, sorry. Sometimes the hands are really abnormal and things like that. And it really struck me, yeah. Uh, Also, like just to give like a similarity between sign language and spoken languages, basically like spoken languages are basically like linear. It's just like imagine playing a piano and you just have to press one key at a time. Because when I speak, I say one word at a time. So I press a key after a person, another key after a person, another key. That's it. That's just how spoken language basically are. They are basically linear. But sign languages, they are more like they have multiple parameters. So it's just like playing a piano where you have 5 or 10 fingers and you have to press the combination of what you press is really important. So you leave from 1 finger to 10 fingers, and it's how you press the 10 fingers that makes sense, and that also makes a note basically. And so you have many things in sign language that happen simultaneously. You have handshake that happens simultaneously. You have body movement that happens simultaneously. You have facial expression that happens simultaneously. They all do happen simultaneously. And it's when you combine all this information together, that's where now you have now meaning to whatever the person is saying. So you can't only look at the hands and guess all what he's saying. No, you can't look just at the face and know what he's saying. He's expressing himself using many components of his body at the same time to vehiculate just one meaning. And in NLP, natural language processing, there has been very few research on sign languages, and the top two conferences, which are like ACL and AMNLP, we see the amount of growth has been increasing. In 2020, for example, like we had like completely zero papers, and for the past 2 years, it's been slightly increasing. And this is a bit weird because this is a language basically. It's really a language, and the top conferences in languages, they don't produce papers about it. So it shows really how these languages are really, really like downlooked or marginalized and things like that. And yeah, and that's also one of the goals of my research, to really put them up front and highlight them. And when you say things in terms of machine translation, um, workshops like the on machine translation have really, really like helped advance the research in the areas. And you see how for spoken languages, the first workshops were around 2006. Meanwhile, for sign language, it just started around 2022, which also shows how the field of sign language processing is lagging behind basically a lot. I will first start by speaking about AfriSign, which was a work I was privileged of doing back in KNUST, which was my bachelor's thesis, as Professor Mo said, and which fortunately won the Best Paper Award at ICLR workshop, at Africa NLP workshop at ICLR 2023. So and I think I would just want to give this paper, the story of the paper basically. So as I said, I was looking for a final year project, and I'd always been interested about deaf people, and I met Marco and everything. And I was like, okay, I just want to work on something like Ghanaian Sign Language translation. I was in Ghana. Ghana was wonderful to me, and I was like, maybe it's time to do something to help Ghana too. But the first challenge is there was no real data set for Ghanaian Sign Language translation. And so you really want to do something, but there's no data set. How do you start? It really becomes complex. But I want to highlight that even some data sets you were saying that there were some data set about sign language or Ghanaian sign language were really data set just about 10 words or just about finger spelling, basically, like characters, alphabets, like A, B, C, D, up to Z, and the same thing in sign language, which is not really like a real data set. This is just like some words or just isolated sign language recognition. That is just to have a sign for A and know that, okay, A means this, B means this, but not a whole sentence, basically. And just also to give some terminologies used in the field. So there's a difference between recognition and translation. Basically, when you say translation, it means like you have a whole video of someone signing. By the way, this is Marco, Dr. Marco. Yeah, shout out to him. This is a whole video of someone signing, and the person is signing a whole sentence, basically. So once you analyze the whole video and you translate it, that is basically like sign language translation, you really have sign language is truly my language, because this sentence or this series of words is grammatically correct. It's in English. So it means that you are moving from the sign language video directly to an understandable form of English. That's sign language translation. Just like you move, I don't know, from tree to English, or I don't know, from Ga to English. It means you really have a sentence that makes sense in Ga, and you really want to have the same sentence that also makes similar sense in English. But recognition is just about when someone is signing, usually he can sign like just one sign. After he's signing one other sign, after he's signing one other sign, after he's signing one other sign. So when you identify these signs individually, you are doing recognition. So basically, like, recognition is just like a word-to-word translation. So you have a sentence in English and you have a sentence in tree, and you take you take one word in English, you translate it to tree. The next word, you translate it to tree. Next word, you translate it to tree. But that's not how translation works. You agree with me at the end of the day, the meaning of the sentence in tree won't make sense because you just did word by word translation, which is different from real translation. And once you identify each of them individually, we call it recognition. And once you identify each of them in a sequence, we call it continuous sign language recognition, basically. So one of the things is sometimes when you're in tech, we have this feeling we can do everything on our computer alone. And sometimes it's wrong because we take data sets which which the people which you are targeting at the end of the day don't feel those data sets are really useful. So that's why it's always important to consult the end users. Because when I started, I remember I was striving, I was like, when is this Ghanaian journal? You always see like this, always one signer down. So I was like, maybe I can take this information from GTV, which is it's a TV channel in Ghana. Maybe I can take this information from GTV and use it basically like as a data set. But then when I consulted Marco, Dr. Marco, who is deaf himself, he told me basically like what most of these interpreters do is not, the deaf people sometimes have uh, difficulties in understanding what they do. So it means we could have translated a whole model on this type of data, and then when they use it, the end user, the deaf people, the real deaf people, it's not working for many reasons. Because you have first, you have what is called spontaneous sign language. And the same way you also have what is called interpreted sign language. I'm sure if I speak tree right now, it won't sound natural. It won't sound spontaneous because I'm just interpreting because it's not my native language, basically. But if someone native from Tree speak from I don't know Kumasi or Ghana speaks Tree, it will flow very well. It's the same thing. Sometimes you have interpreters, but the way they do sign is not exactly the same way like a deaf person will also sign. So I was asking, okay, how can I then take a data set? And he was like, there's this Bible on this website called Jehovah Witness, and they have good signers there. Basically, like most of the people who were signing for those videos are my friends and are my including me. And I was like, wow. So he validated and he advised me to use this resource. So basically, this is how it looks. So you basically have a deaf person or someone who really knows sign language very well, and he's just translating a, a Bible verse, basically. And from this, when I finished extracting the data from these people, I realized how I could form a data set of Ghanaian Sign Language, which had approximately like 2,500 samples. And I divided them into 2,000 samples for the train, 230 for the dev, and 203 for the test set. But still, this data set was very small compared to, we know how these machine learning models, they are very data hungry. So this was a very small sample to really work on. So I went back again to Marco and I asked how this data is good, but it's small. We need a bit more because these models need much more data to start producing something. And then he was like, oh, if it is small, I know like a lot of sign languages around Africa, we share a bit some similarities. And then after they now explain to me now the history of how American Sign Language and many African sign languages, they are joined because there was Andrew Foster, who was a Black American at Gallaudet University. Gallaudet University is a university in Washington, D.C., and it's a deaf university, basically, for deaf people at Gallaudet. So Andrew Foster, who was a Black American, came back to Africa. In fact, he started from Ghana, he came with educational materials in sign languages so that the deaf communities in Africa could learn education, could be educated, because all the materials we had were in English and things. But he came with materials which were now in sign languages, so in American Sign Language. So it means that we had communities in Ghana, like the Adamoro-based community. Sorry if I mispronounce it wrong. I think it's around the eastern region of Ghana. They had sign languages themselves, but when he came with these resources, this sign language, these local sign languages that they had, started blending now with the American Sign Language, forming some new sort of language, which is an intermediate, which is now where now Ghanaian Sign Language now came all about. And the same way he was in Ghana, he then later moved to Nigeria, and he moved to other parts of Africa, like trying to educate the deaf people there. So it means that those countries now then having now some sign languages and some materials to study, to be educated in sign languages. That's one of the reasons why some of these countries, they do share some similarities in their sign languages. So I was like, okay, maybe I can expand the project. Instead of looking at Ghanaian Sign Language, I can look at African Sign Languages, because they seem to be sharing some similarities. Not they're not exactly the same, but they do share some level of similarities. Basically, they come from the same language family. And also, like back in those time, all this thing about multilingual was trending. So I was like, maybe I should just expand, because multilinguality has proven to be sometimes better. So that's now how I now took now from the same source. I now form now dataset now from Ghana Sign Language, Nigerian Sign Language, Kenya Sign Language, Zimbabwe Sign Language, Zambia Sign Language, Zimbabwe, South Africa. And of course, we had ASL, which was the American Sign Language. And this is Phoenix. Phoenix was a standard benchmark dataset from from Germany, which is not from here, but it could just help us know how our dataset was comparing to the standard benchmark dataset back in those times. And it increased the dataset significantly. And as you can see, in terms of duration, in terms of average duration and things. And the same way we have like this big contrast between English and African languages, is the same way. Here you see how you have much more data for American Sign Language than for the other sign language. But we can use this data as a pre-training and now fine-tune now on this smaller data. Basically, that was my idea back then. Yeah. So I was like, though it's a different sign language, at least because the amount of data there is sufficient, maybe I can use it in one way or the other to improve my targets, which are 6 African sign languages. So we have our data and we compared it to previous data, mostly from American Sign Language, British Sign Language, Chinese Sign Language, Korean Sign Language, and German Sign Language. And you see in terms of the number of hours, ours was not that bad, basically, yeah. So once you have the data, you need now the next thing, model building. And for the model, I was basically like trying to do something just simple and which I believe would be effective. So we know how we have transformers, basically like encoder decoder models, and basically like transformer usually takes some tokens or some basically like a series of vectors, and basically like you take a video of someone signing, you pass the video through a human key point extractor. This is off the shelf, means that it has already been trained. You just use it as a model, you feed it an image, and it gives you like a vector like this, just having the key components of the person. You can see how it looks here. So once I feed this image to a human key point estimator, I'm going to have like basically like these coordinates or this sort of vector, which I can now put in a linear form. And I pass each image to this, and I get a vector for each image, and I now pass it now like to a transformer an encoder-decoder model. Yeah, so I pass it to an encoder-decoder model and I get now the final version, which is now like a text language, which in this case, English. So we build different types of models. Here we build like a bilingual baseline where basically like a bilingual baseline means you train from maybe Ghanaian Sign Language to English, a Nigerian Sign Language to English, uh, Zimbabwe Sign Language to English, but separately, independently. And you also have a zero-shot setting. Basically, like zero-shot, we mean like we have a model trained on American Sign Language, which has never seen anything about Ghanaian Sign Language or has never seen anything about any other type of language inside the data, inside the training data set. And we now use that model now, and we now fit to that model now other languages. Basically, we fit to that model Ghanaian Sign Language, any other language. But that model had never seen those languages. That's why you call zero shot. Means that, yeah, this is the first time it sees this type of languages. Or you can fine tune the ASL baseline, means like you train a model on ASL, and then you fine tune it on the mixture of languages. Here you fine tune it individually, and here by multilingual training that you take this same ASL baseline and you fine tune all the languages you have, the African Sign Languages you have, you put them as one data set, and you fine tune this ASL model. And basically, like, the results were showing that we do gain when we do this type of fine-tuning, whether we do individual fine-tuning on each language pair or we do a multilingual fine-tuning. But the multilingual fine-tuning produced a better score of 1.93 blue score. And as you can see, like, these blue scores are very, very extremely low, which shows how sign language is really, really like it's really complex for these models. Because when you look at text translation, that is maybe like, I don't know, from English to German or whatsoever, the blue score is usually like very high. Like you sometimes have things like 30 blue score, but here you have something like 1 blue score, which is order of magnitude less. And this also shows how challenging sign languages is, and this type of scores were also gotten by World Machine Translation Shared Task on Sign Languages. They're also getting similar range scores. So which shows that the problem was not maybe from maybe our data or whatsoever, but it just shows how the challenging nature of translating sign languages, basically. Some of the limitations in our work back in those times was you had cross-contamination. Basically, like you have a verse, imagine you have a verse like in Kenyan Sign Language and you have the same verse. So in Kenyan Sign Language, you have the verse, which is like in the trained data set, and maybe in Ghanaian Sign Language, you have that same verse, but which is in the test data set. That's why we call cross-contamination. So it means that you have the same sample in different languages, but they are in different parts of the split. And it was also like on limited domain, it was just Bible. And the type of tokenization we use was pose estimation. Basically, as I was showing, we were just using like this type of vectors, but they are limited somehow. We are going to look at it again further. The takeaway was that we need more sign languages in the sign language processing research community. That's basically because I think it's like 70% of the deaths in the world are found in low and middle income countries, but most of the research on sign language is for sign languages from high income countries. So we do need more because this can benefit more people from low and middle income countries. And we can take a lot of inspiration from low resource machine translation. Basically, like the idea of fine-tuning, the idea of transfer learning, the idea of multilingual training. These are all ideas taken from low resource machine translation. We should include deaf people in our research because once you include them, you gain a lot of insights and basically you know like the way forward. The same way like if you do a research on tree, you should include people who speak tree. You should include natives from those languages. They do help you and they do give you valuable advices. They do give you valuable data sets. And you should have an extensive documentation of sign languages needed. This information on how different sign languages from Africa were related, uh, some some languages from Africa are related, was basically like was like a mouth to ear information. Basically, I got it from a deaf person. And we should document this type of things more so that people all over can read this type of articles and they can know how the way forward might imply more linguistics coming into the field. Yeah. Then the next work I did, which got published at EMNLP conference, was JW Sign, which was now like a bigger data set, not just on African sign languages, but now on like 98 sign languages. And this is the largest data set right now we have on sign language processing. And this work was done in collaboration with some folks from France and the US and Zurich and Matthias Müller. Basically, like we have 300 plus sign languages all over the world, but 80% of hard and hearing people live in middle and low level income countries, according to a report by WHO. And research on sign language from these regions is rare. So it's a problem, I thought. So I was like, we need to raise these languages, basically. So how can we give an initial data set to these sign languages and make them more visible? Yeah, because we always have this excuse of like, oh yeah, we don't have data, we don't have data. But if you make these languages visible and you are like, come on, you can't just be only working on American Sign Language or German Sign Language or whatsoever. The winners here are always from America and this type of countries, but the left behind, you have a lot of low and middle income countries which are left behind. And this problem is not only in sign languages, it's a problem which touches also like spoken languages or written languages, where you have a lot of work from high income languages and not much work from low income and middle income countries. One of the reasons why we have the birth of companies like Ghana NLP and products like Kaya, which I really appreciate, by the way. And we see how the Bible has had an important role in NLP and a very, very important role in NLP. The Johns Hopkins University, they had these corpus of the Bible corpus for text in many languages, which help boost a lot of research about text languages from different parts of the world. And from CMU, Carnegie Mellon University, they had also this type of same data set for speech data set, the CMU wideness data set, which was also on Bible. And we can see how the Jehovah Witness or the Bible translation, they have translated the Bible in many different languages by going to those countries and by speaking with the deaf communities of those countries and by trying to translate the Bible from their Bible into the different sign languages all over the world. And so we formed this data set, which was very diverse. We had basically like representation from all the 7 continents of the world. And you can see here the language statistics pair. Of course, we have some languages have a lot of data and it goes down, but at least we now have some level of initial representation, although we need again to do more work for this language, but at least it's a start, basically, yeah. And you have sign diversity. We know there's always like this issue of sometimes you train models on some races of people, and later on, if these models see different race, they basically become biased, basically. Yeah. So the goal here was to have like people from different colors, different shapes, different races, and things like that, which is very important. And when we compare this other data set, as I was saying, we have 2,500 hours, which is the largest data set right now. We have 1,500 signers, which is like the largest we have, and everything, which at least is a good start. And we also want to make like a disclaimer: we do not of GW data. Basically, we help the community by providing links to this data, which they can use for research. But yeah. And now I'm going to speak about a much recent work I did at the Toyota Tech Institute of Chicago with the collaboration of Sheldon, Greg, and Karen, basically. So now you switch gears, and there are two main approaches in sign language translation, which you want to like state of the art, basically. On one side, how do you represent sign language? That is basically how do you take representations from sign languages? How do you have a video of sign language and you can have a vector out of it? I think that's where the main difference in ideologies have been coming from. On one side, you have folks who use like the media pipe library. Media pipe library is basically like this. So you feed in a video and you're going to have like some mesh representation of a face. So you have a vector for the face, a vector for the body, and a vector for the hands, basically. That's the media pipe component. That's what you call by media pipe. And it's an off-the-shelf library. So it means you can just do like, I don't know, pip install media pipe after you import media pipe, and after you just play with it normally. Yeah. You don't have to train anything. It's basically an API also at some point, yeah. And this approach, MediaPipe has been developed by Google, and this approach formed the principle of Google's publication at NeurIPS last year. So what they did is they take the video frames, they pass it through MediaPipe, and for each video frame, you get some landmarks. After with the landmarks, basically by landmarks, I just imagine vectors, basically, yeah. So you just take, so imagine you take these vectors an XY coordinate. This one's an XY coordinate. So you combine all of them. And for this whole image is the combination of all these vectors or all these vector coordinates, which are going to be the representation of this frame. So you pass each frame, you get some landmarks or some vectors, you normalize these landmarks, and landmark reduction and normalization. By reduction, they mean like, so if in 1 second you have maybe like 30 frames, for a video of 30 frames per second, now they are just going to take 15 frames for 1 second. They do that by taking one frame, you skip the next frame, you take one frame again, you skip the next frame, one frame, you skip the next frame. That's because in video, there's a lot of redundancy in information across the frames. And now you use a linear projection, just like a linear layer or I don't know, an MLP, and you pass it to a T5 base. T5 basically like it's a pre-trained model, an encoder-decoder model. So basically like the goal of this linear projection is just to map like this type of input to what the input that, to the form of input that T5 is used seeing, is used to see usually, basically. And you get an output, basically. So this is what this is Google's principle, basically, like people from Utuse at NIPS last year. We also have on the other side, you have a much more recent paper from Meta, which came out this year, 2024. And the goal now here is instead of using media pipe, now here they use like an encoder, basically. They call the encoder sign hierarchy encoder. But the overall gist is just what? It's just like you have some videos, and this is, so you have the video, you mask some components of the videos. They use some sort of mask language representation or mask video representation in this case. So you have a video of someone signing. You mask some components of the video. You now take now the unmasked components. You fit those unmasked components to an encoder, which is just call it sign hierarchy encoder, but just consider it just a normal encoder. They feed it to an encoder. And the goal of the decoder now is to reconstruct the whole image just from what he has seen, just from this masked, just from this unmasked portion. So you give a model like maybe like, let's say 20% of unmasked patches, and the model has to reconstruct like the whole video, like 100%. And once the model knows how to do it, the model understands the video somehow, because if you mask some things and the model can know what the masked things are, means somehow the model has some level of understanding, yeah. And now, once you have finished training this encoder, actually they call it sign hierarchy because there's a hierarchy encoder, which is just like a T5 base. It just means that it's just a pre-trained encoder. That is a start from that as an initialization point, and hierarchy was trained on normal videos. So you start from that as an initialization point and you continue pre-training from there. And now you now take down this encoder and you now feed it here. Sorry. You now feed this encoder here. And now for the downstream task, so this was the first part, self-supervised video pre-training. The second part is supervised sign language translation. So you feed this encoder. So you now take now the original video, you feed it to this encoder, you get some features, you pass it again through a linear layer, you pass it again through T5, which is always also another pre-trained model, and you now get now the text or target translation. So you can see how these two components, they share, this part is similar. That is, you always get some type of features or input, and then you have to pass it through a linear projection, then pass it through a T5, then you get an output. It's the same thing here. You get some type of input, you pass it through a linear projection, then through T5, and then you get the text. The only difference is which input do you pass? Which representation do you pass, in other words? Here they pass landmark coordinates taken from this type of model, and yet they learn these features basically using like this mask mask autoencoders, representation learning. But this step of learning this type of representation is very expensive. It took Meta 64,880 gigabyte GPUs for 14 days. This is crazy amount of resources to do just this part, you see. So it's not bad, but at the same time, it's very computationally expensive. But you are trying to move more and more into efficient methods which are affordable. You can agree with me, few people can do this type of work. Few people have the luxury of having this amount of resources or having this amount of GPUs. So that's now where now say sign musketeers come in place. So the goal was, how can we reduce this amount? Because pre-training is good, but how can we reduce drastically this amount of pre-training? Because you have one pre-training that for 64,800 GPUs. Of course, we can't afford that. Even in Chicago, we can't afford that. So, but how can we then do something? So we're like, we base ourselves on the linguistics of sign language. The linguistics of sign language tells us that the face, the hands, and the body motion, that's where all the information is needed. So we don't need this background, we don't need any other information. We just need the relevant information. So the idea was, let's learn some representation of faces, learn some representation of hands, And why do we have to learn this is because the type of facial expressions and the type of handshapes we see in sign languages, they are very different from the type of expressions or handshapes we common maybe hearing people or hearing people do. So even if you have a model that has been trained on hands, the type of hands in sign language, they generally have some complex handshapes. So we want a model now to understand this type of handshapes. We want a model now to understand this type of facial expressions, which are unique in sign languages. So to train these components now, so I'm first of all going to highlight this first part, our self-supervised pre-training. So to train this, we use a Dino V2 pre-training. Dino V2 basically like it's a model from Meta also, but that's for images basically. So it's a model that you feed it an image and it gives a representation of that image. So we're like, okay, we now want to feed now, we want now to pre-train now this model now, but on hand shapes. So from our data set, we took like 1 million hand shapes. And we trained a model, just random hand shapes from the data. Just crop the hands, and so we feed a model this type of hands. And it learns using this self-distillation method. So basically, like, we have two models. We have a student model and you have a teacher model. The student model sees just some local views of the image. By local views means like maybe you take a random crop, but a very small crop, which is generally like 25% of the image or less. I think in our case, we took like 50% and less. So we take a crop of the image. We have to give this student model 8 crops from this image. Random crops, but very small crops. So that's why you see how we have these crops here. And those crops on the image. And then you have the teacher model, which we now give global views. So these are local views, very small views of the image, and these are global views. So you take like a bigger crop, a larger crop from the image. So, and this, we just have 2 of these views. Now, the teacher model sees just these global views. The student model sees both the global and the local views. The goal is that at the end of the day, this model and this model should have the same representation because all of these images, they come from the same image. So if the model is sufficiently trained well, or if the model is really good at representing, he should know that if I give you different views from the same image and I give you, again, different views, but larger views, also from the same image, you should know that they all correspond to the same image somehow. So basically, that's just like a very brief way of how we train this. So yeah. So after now training these models, so we train 2 of those models. We train one for the face, that is we feed 1 million faces to this model. Then we get a Dino V2 for the face, and then we feed 1 million hands to this model, and we get a Dino V2 for the hands. So now you have a face Dino V2 and you have a hands Dino V2. Now, once you now have a video now, you now use now a face detector. We take the face, we take the information, we take the crop from the face, we pass it now through our Dino V2, which we have pre-trained, and we freeze this here. So here it's frozen at this point. It gets now we have some latent representation. We do the same thing for the hands. We feed them to this model, we get 2 representations. And now for the whole body now, because an important information is how the movement is done, and also like how the relationship between the 2 hands and things like that. We now get just 7 pose or key points from this image, just to represent like the structure of the body of the person at this particular point in time. So you have 7 key points and you have this. We now feed these 7 key points now to a linear layer or just a 2D coordinate projector, which is basically like just a linear layer, as I was saying. You feed it and you get some other type of representation. So at the end of the day, you have 4 vectors representing 4 different components of this image. Now, so now this video now becomes basically like this. So you have, this is for the first frame, the second frame, the third frame, and etc. Now, once you now have this, remember that the only difference is the type of features you are trying to search. So now have a fair comparison with the works from Uthus et al. And Ross et al. We have to keep these components the same. But now you have to prove that with this new type of features we can get, which is not from one, which is not from the higher encoder or this type, we now get better scores. So we feed this to another linear layer also. We feed it another T5. The Llama GPT is this is basically like an ongoing work, but we feed it to the same T5, and we have to get now the text. And shockingly, the most interesting part is by doing this, we slash the computational resources drastically. You can see that this is our models. Our models are in blue, and the models from Rust, Meta, they are in yellow and red. And you can see how, in terms of GPU hours or in terms of computational resources we just use like a very small amount of GPU hours. And for our best model, we can see how when we see the next best model, a model that competes with our model, it uses like 200 or 20,000 GPU hours. Meanwhile, this doesn't even use even up to 1,000 GPU hours. So you can see how our model is very, very, very efficient in learning. And in terms of the blue score, it gives similar blue scores. And another thing too is that once you see YouTube 5, it means the amount of pre-training epochs we did. We only do 5 pre-training epochs using our methods, but their models use like 200 pre-training 200 pre-training epochs, and they have a lower score, and the model which competes with us uses 800 pre-training epochs. So we use 200 or we use a significant amount of pre-training epochs less than theirs. They use 800 pre-training epochs. We only use 500 pre-training epochs. Secondly, the size of the dots of the bubbles represent the amount of data we use during pre-training. Remember, I said we only use 1 million data for pre-training. Meanwhile, these their models use 50% of the data, which is close to 44 times amount of data during pre-training. So that's why you see how the size of the bubble is bigger. So our model first has lower computational resources, uses less pre-training epoch, and also uses less pre-training data. And it becomes affordable to common labs or known big tech companies. And we can see how on the best setting, that is, you pre-train on YouTube ASL. YouTube ASL is basically like a data set of around 1,000 hours, and we fine-tune on how to sign, which is basically a data set of around 70 hours. We see how the model from Rust, which is like the meta model I was showing, gets a 14.7 blue score. And on the same setting, our model gets a 14.3 blue score. So you just have a difference of 0.4 blue score. But in terms of GPU hours used, we can see how ours is 880 and theirs is significantly more. We also note that their pre-training, they also used the test or the target data set during pre-training. Meanwhile, ours didn't use the target data set during pre-training. And also in terms of the number of frames, we only use 1.2% of the frames, and they use 50% of the number of frames. And we might also ask ourselves, we do now some ablations. In this setting, we might ask, what if we feed this whole image image and get another channel, maybe somewhere a fifth channel, which contains information from this whole image. And you saw that when we do this, when we add this information, it doesn't help. The scores go down. Basically, it's this. So, or maybe I should have started from this one. So this row, basically, so it means you have uncrop plus original INOV2. By uncrop, we mean that we take like the whole image, that is, you don't crop it into different crops, you take just like the whole image, you pass it through a Dino V2, you get some representation, you pass it now through the linear T5, a linear layer, a T5 to get now the output. But this has a problem. This doesn't perform very well. You can see how the blue score is 4.9. So we conclude two things from here. The first thing is we need to crop the video into different components. That's why we call it multi-stream. Basically, like you have 4 different streams of information which are coming separately and independently from each other. And the second thing also is that you need to fine-tune this Dino V2 because in the first setting, we were only taking these original frames and passing through the non-fine-tuned Dino V2. That is, you just take an off-the-shelf model and just use it like that. No, you need to fine-tune the model or continue pre-tuning the model so that it knows how the information of this type of hands, this type of face are important. So yeah, once you use an uncrop image and the original Dino V2, your blue score is 4.9. But once you crop the image and use the original Dino V2, the blue score moves now to 11.3. So it shows that here, the multi-stream approach, that is just cropping images into different, just having an image and identifying the 4 different components in the image is very essential to understand, to have a good sign language understanding. And we now ask ourselves now, what if now you now take a global frame? That is, you take the whole frame, as I was saying, and you add it as another channel. And you can see how they're compared to when you don't use it, because here you also have a pre-trained Dino V2, you have also a pre-trained Dino V2, but here you have a global frame, and here you have no global frame. You can see how when you don't have a global frame, the score is higher, which shows that it's not just about adding any information. It's not just adding a lot of information doesn't always help. Sometimes you need to add, you need to know what to add exactly and how to add it so that it now improves the scores. Yeah, I think during my presentation, I just wanted to thank you all.
All right, thank you very much, Shester. Thank you very, very much for this nice presentation. Yeah, so some of the questions are already coming. I'll ask them, I'll read them out for you, or you can read them in the comment section and then maybe give us an answer. Or if you want to ask your question, you can unmute yourself and ask as well. But firstly, as we could see, issue of data was really critical. So far, the data you have used, apart from JW sign, has been also how to sign and then YouTube ASL. How did you get this YouTube ASL?
Okay, so YouTube ASL is data from Google, and it's on their GitHub, basically.
Oh, okay, oh, okay, oh, okay, okay.
Yeah.
Okay, so this is already collected data from Google.
Yeah, so
And then what about the how to sign?
it's also another data set from, it's also online on the,
Oh, okay.
they have a web page for that.
Okay, good. All right, so I'll
And
read some questions that are coming in. Question 1 is from sign language to speech. I think I've seen, Lawrence, I've seen some articles on sign language to speech already. Even there are some works already I've seen online on sign language to speech as well. So, but I've not really read them fully. I cannot also tell. Chester, do you have any idea on sign language to speech?
Oh, yeah. Sign language to speech, I think the challenge is just about data alignment,
Yeah,
because most of the data we have, just, I don't know, let me just, I hope my screen is still visible.
yeah, your screen is still visible.
So you are seeing the YouTube image?
Yeah, we are seeing the YouTube video.
Okay, sure. So when someone is signing, generally, you have captions of what the person is signing. And these captions are made by by the native signer generally. So the alignment is right. So it's not debatable. But once you move from sign to speech, we don't have a lot of data where you have someone signing and you have the corresponding speech. So in that case, if you want to move from sign to speech concretely, we need to move from sign to text and then text to speech.
Okay.
I think that will cross the gap. But internally, at the backbone, you have a sign to text and then text to speech, which is possible. But
Yeah,
moving
that's also
directly from
possible.
sign to speech, you don't have that data. But I think the
Okay,
other direction is possible. Yeah.
okay. Lawrence, do you want to ask further question? Maybe I'll read your other question as well, and if you can come in. And then he says, what about sign language directly to local languages?
Yeah, it's also
It's the same. It's the same
it's the same,
basically,
yeah.
right?
I
It's the
think
same.
it's just a problem of data alignment. So we can
Yeah.
have, I don't know, sign language to English and then English to Twi. It can
Yeah.
happen. So a backdoor, the backbone of the model can be like that. But directly, if you also have, it's just a form of data, basically, yeah. Data alignment.
The data alignment. Okay. Okay. Then the other question was your experience with the T5 model. Is it the same as T5 from? I think it's Microsoft, right?
No, T5 was by Google.
T5 is Google, but is there another type from Microsoft? Is that what the Lawrence are asking for?
Steven, I think I don't know if you can hear
I,
me. It's a bit noisy in the background. Can you hear me?
yeah, I can hear you.
Oh, okay. Yeah, I'm just confusing the two different models because I know Microsoft has a T5 model, so maybe it's a different one. So that's okay. No problem in that case then.
Okay. Okay.
Just
So
just go back to my previous question,
uh,
if I can. Can I go back
yes, go
on that?
ahead. Go ahead. Go ahead.
Yeah. Because from the frame you showed, thanks for your presentation, Shester. That's really interesting. Really enjoyed it. The question about sign language to speech, I think I'm missing something here because the frame you showed, it showed the sign and then the text. So I imagine that could contribute like a part of your data set, correct? You know, the sign and then the text that was written underneath. Is that correct?
I think I didn't get the last part of what you said.
You just showed an image of a lady and
Yeah,
then the text that was underneath it when you were
yeah,
trying to explain the problem, exactly this one.
yeah.
So could this frame be considered a part of your data set? So like the image and then the corresponding text underneath it? Or it's just a series of frames that make up like one example of your data set, for instance?
Oh, it'll be a series of frames, yeah. So there's a way of knowing if when a woman is going to be signing at some point, as you can see, the text changed. The text changes. So we crop in time. So
Okay,
we crop in time. So if we have a whole video, it's part of the metadata of the video, basically. We have that
exactly.
information from the metadata of the video, yeah.
Okay, so in building a data set for sign language to speech, I mean,
Yeah.
if you have the speech as the target label, sorry, if you have the text as the target label, what stops you from replacing that text by just the audio of that text?
It's so basically you are saying we are going to have like a model that's going to give us a speech of that text, right?
Yeah, exactly.
Yeah, it's possible, it's doable, but at the same time, you now have to rely on how good that model is. Because if that
No, but
model gives a wrong speech, this other model also give a wrong. So it depends on how good the targets are going to be. But I agree with you here. We can have a model that takes text and gives speech, and now the goal now is now to have sign to speech.
okay, that's understandable. Okay, that's fine. Thank you very much. I appreciate the presentation. Thank you.
Sure, no problem.
All right, good. Any other question? Anyone with a different question? Okay, so if there is no